Hi everyone, I'm Ashley Joe and he's Connor Ho. So our project topic is about the sunspot object detection. Our main purpose is helping scientists to identify if there's a sunspot in this hemisphere shape of photo. We call it hemisphoto here. The reason why the scientists need to pre-processing the hemisphoto is because they will put those photos into an analyzer software called gap light analyzer to calculate the ratio between trees and open sky. If there's a sunspot in the photo, it tends to affect the result by overexposing the region nearby. As you can tell on the right side of the graph, the gap light analyzer identified the sunspot as the part of the open sky. And we are here to identify the spot and let the scientists decide how to deal with it, either deleting it or do a further modification. Here, we pre-process the dataset by labeling the data as follows. The label column indicates if there's a sunspot in the photo or not. If there's a sunspot, then it's a 1, vice versa. For the photo that do have the sunspot, we record the label of the bounding boxes and calculate the correlated size of it. For the one do not have the sunspot in the photo, it just denoted at the value as none. Before we even get into the how we processing the XTrend dataset, we want to briefly mention how YOLO algorithm works. YOLO stands for you only look once, and as the picture on the left side shows, YOLO can detect the item in the picture and even further categorizing it. At the right side, YOLO map out the photo with the fixed size of grids and label through them with the correlated boxes information. For our XTrend dataset, we compressed our photo from 2700 by 2700 pixel to 900 pixel times 900. And then we using the same concept from YOLO. We map out the photo with the fixed size grids. Here we using 180 by 180 pixel for the grid box for each image photo. It further divided the picture into 5 by 5 grid boxes. As you can see from the example, if there's a sunspot in the picture, that specific box will denoted as class 1 in the labeling, and every other box will denoted as class 0, means there's no sunspot in it. Due to the essence for the sun, there will only be one sunspot, but 24 non-sunspot per photo. And that's how we get our data set.
So now that we have the training data, we're going to build a model. The model that we chose has 5 convolutional layers and 3 dense layers. And this is the architecture that we went with, and it seemed to work the best for identifying sunspots. As we trained the data, we used focal loss because there was a high imbalance in the classes of our data because there was only 352 small boxes or anchor boxes that have a sunspot in them, while there's over 13,000 boxes that were just background class. So the model could just predict everything to be background and it would get a very low loss and it would think it was doing a good job. So focal loss downweights it when it gets the background class wrong, and it weights it more, it charges it a higher penalty, if you will, when it gets the sunspot class wrong. And I don't want to get too much into the math here, but that's how we deal with his class imbalance. And so after training our model and predicting on the unseen data, we built a ROC curve because our model outputs a probability that each box is a sunspot. So it doesn't predict 0 or 1, but it says there's a probability that this box is a sunspot. And you can see under the row curve is a point 0.95 area, and that's so it's suggesting that it's much better than just random chance. However, precision recall curve is better for imbalanced data sets, and it's only zero point 0.3 under the precision recall curve for the area underneath the curve. So it's not, suggesting it's not the best model yet. Um, so we used 40% of the data just left out unseen for the testing. We ended up using a threshold of 0.14 probability or higher to choose it as a sunspot. So if the model predicted 0.14 probability or 0.15 that this was a sunspot, then we said yes, we're going to label it as a sunspot, being predicted as a sunspot. It detected 63 true positives. So there's only 68 um, sunspots in the testing data, and it detected 63 of them. It missed 5 of them, 5 false negatives, and it predicted 872 false positives. So the 872 extra images, little anchor boxes that it said, yes, this is a sunspot, even though it wasn't. But there were still 4,500 background class anchor boxes that it predicted correctly, the true negatives. So it's a pretty good ratio there. We wanted to check out what was actually happening in our model. So we wanted to plot some of these predictions. So this is a correctly classified sunspot by the model. This is another correctly classified sunspot by the model. This is uh, not a sunspot, but the model thought it was, and we think it's because a circular type thing here. This was a sunspot that it missed. And we think it's really small. There's only 5 of them that it missed, and this is one of them. And the other 4 are very similar to this. They're very small sunspots that they missed. And then another reason we got a lot of false positives is I think this image demonstrates it. It predicted all these red boxes as sunspots. I think we didn't have enough data where we had random open sky or like random neighborhood type things. So if we had more data to put in there, it could have learned that these are not sunspots. And also if we just limit the prediction to 1 per photo because there's only one sun, obviously, then that would have helped our false positive rate a lot. So in conclusion, this is not quite ready for the industry. Like maybe the logging industry would want to use this for their gap light analyzer to see where the log, or like scientists use this. But it's not quite ready. There's too many false positives. So I think if we can get much more data and just tweak our parameters a little bit more, hopefully we can get to that point someday. So yeah, thank you so much for watching.